Hello friends, welcome to lecture number 3 of our second week where we are developing the fundamental equations for conduction. In the first lecture you were introduced to the concept of thermal conductivity and thermal diffusivity, and then in the previous lecture we developed the generalized form of the heat diffusion equation in Cartesian coordinate, and today we shall be continuing with that to develop the equations in the curvilinear coordinate systems. But before we do that, just a recap of whatever we have done in the previous lecture. We have developed the generalized heat diffusion equation or generalized heat conduction equation. I mean, assuming conduction as the only mode of heat transfer inside some kind of medium, we have developed the generalized energy transmission equation of a form like this: dou dou x of kx dou t dou x plus dou dou y of ky dou t dou y plus dou dou z of kz dou t dou z plus qz dot triple prime, which is the volumetric energy generation rate per unit volume of the medium, is equal to rho c dou t dou t. Quite often instead of C you can write also Cp. This refers to specific heat. For solids and liquids we know that there is only one specific heat that to be considered, but for gases we have to consider two different specific heats. So, you can write this one as Cp, but for I shall be sticking with the notation just C only to denote this one to be the specific heat of importance. So, we already know the meaning of these three terms, or rather the 5 terms involved there. The first 3 terms on the left hand side corresponds to the heat diffusion in all the 3 coordinate directions x, y and z. Here kx, ky and kz refers to the thermal conductivity in different directions. If we are talking about an isotropic material, then kx, ky and kz are equal to each other, and thankfully most of the materials that we deal with are isotropic in nature, but there may be certain exceptions, like the example of graphite I have mentioned. Its thermal conductivity along a particular layer and perpendicular to the layer, they are widely different. The fourth term Qg or triple prime, as I just mentioned, it is the volumetric energy generation rate. In certain limited cases like nuclear materials etc., we may have this term of importance, but in most of the cases this is not present at all. And the last term, that is the term on the right hand side, refers to the rate of change in energy content or time rate of change of energy content of the medium. For steady state situation, this term is equal to 0. And there are different boundary conditions also that I have mentioned. We may have broadly 3 kinds of boundary conditions. I repeat the diagrams that I am showing here. These diagrams I have taken from the book of Intropina and Dewitt, as which is the primary reference book for this particular course. So, the first kind of boundary condition where we have the value of the temperature is specified, which is called the Dirichlet boundary condition or boundary condition of the first kind. Second is the constant surface heat flux boundary condition, which is also referred as the Neumann boundary condition, where practically we have the temperature gradient, this dou T dou x, that is specified. A special case of that one can be adiabatic boundary condition, where temperature gradient is equal to 0, and a boundary condition of third kind can be convective or radiative boundary condition, where we go for a balance of conduction heat flux and convection or radiation or maybe both heat fluxes at a particular surface. So, depending upon what kind of problem you are dealing with, we may have to deal with different kinds of boundary condition. And also the 3 boundary conditions shown here, these are all boundary conditions, but if you are solving a transient problem, you also need the initial condition, that is we need to know the value of temperature at all the points or throughout the domain at time t equal to 0, that is the time where you are starting your calculation. And there may be several simplified form of the heat diffusion equation that you can have, like a particular one of interest if we are dealing with a steady 2-dimensional and no heat generation situation. In that case, let us say Z is the component that is not of importance, then in that case the equation reduces to a simple form. Like this, and if we are talking about an isotropic material, that is kx equal to ky, then an even simpler form dou 2t dou x2 plus dou 2t dou y2 is equal to 0, or you can say the Laplacian of temperature is equal to 0, which is the Laplace equation. Of course, we can get the Laplacian or Laplace equation in 3-dimensional form also. If we are talking about a steady state 3-dimensional flow situation, or sorry, heat conduction situation without any heat generation, and for isotropic material, then we shall be getting a 3-dimensional form, the Laplace equation. And if we are talking about steady 1-dimensional no heat generation and isotropic, then it becomes even simpler. Then your equation is just an ordinary differential equation instead of partial differential equation, it is an ordinary differential equation of this form. So, depending upon the order of the equation, we need multiple boundary conditions, and these boundary conditions are of the 3 types that we have mentioned. Now, the Cartesian form of heat conduction equation or heat diffusion equation is very much applicable whenever you are dealing with a system where rectangular coordinate system is applicable, like heat conduction through a block, maybe heat conduction through the walls of your room, heat conduction through a large cube of ice, something like that, or a long metallic bar, etc. But if there are maybe several situations where we have to go for a curvilinear coordinate system, like suppose you are having a cylindrical bar or a cylindrical rod, and you want to estimate the heat conduction through that. Now, because of the shape, the rectilinear coordinate system or rectangular coordinate system rather is not applicable there, and we have to go for the cylindrical coordinate system. And therefore, we need a modification in the basic heat diffusion equation that we have developed here, and that is why let us check out the heat diffusion equation in cylindrical and later on in spherical coordinate system. So, first we have the cylindrical coordinate system. This is the problem statement that is given to us. We are having a cylinder just like shown here, and we want to estimate or we want to develop the heat diffusion equation inside the cylinder. So, to take that, just the way we have done for rectangular coordinate system as well, from the given domain we have assumed an infinitesimally small volume. Similarly, here also an infinitesimally small volume within the cylinder that has been identified, and the zoomed view of that one is shown on my right. Now, the coordinate system is important. Look at the coordinate system that is shown here. X, Y, Z is a traditional Cartesian coordinate system, but here we are going for r, phi, z, where r refers to, here z is the same because the z coordinate direction remains unaltered. R refers to, like if this is your point, if we take a point, or rather if we take a projection of this one on the xy plane, this is the projection, then r refers to the distance of this point from the origin of the coordinate system on this xy plane. Like in this particular diagram, r is shown here, but it could have been shown here also. R refers to this vector which starts from here and finishes off here, that is, it is entirely on the xy plane. And phi is the angle it is making with the x coordinate system. Phi is the angle this r is making with the x coordinate direction. So, now we have a zoom view of this particular volume that we are talking about. Let us try to identify the dimensions of this one. For rectangular coordinate system, it is very easy. In this case, we have to be careful. It is not at all difficult, but just carefully observe all the terms and try to relate or try to express the length of each of the faces or each of the edges in terms of r, phi and z. We now know the definitions of r, phi and z. I repeat again, here z refers to, like if this is the point, then if we take a projection of that one on the xy plane, then we arrive at this particular point. Then z refers to the vertical distance between the original point and the projection, that is this particular distance is your z, which is parallel to the z coordinate direction, and r refers to this particular vector, that is r refers to a distance of this projected point from the origin on the xy plane, and phi is the angle this projection is making or this r is making with the x coordinate direction. So, for the infinitesimally small volume, let us say this position refers to the radius r. So, it starts from point r and let us say it finishes at point r plus dr. Accordingly, this dimension is dr, rather here the dimension is r, here the dimension is r plus dr. Accordingly, length of this edge is dr. Then how can we identify the others? It is straightforward. We can easily say this one is will be equal to dz, or rather it is shown on the other side. this one is equal to dz because this is parallel to the z coordinate direction, and we have to identify now this particular one. To identify this, let us try to identify, we know that this particular length is r, and then we are having an arc of radius r that is traversing an angle of d phi in the azimuthal direction. So, the length of this arc can be equal to r d phi, assuming phi to be sufficiently small. So, accordingly we are getting the 3 edges, this one is equal to dr, this is equal to dz, and this is equal to r d phi. Then the volume, say dv, I am putting this v, I am crossing this v to indicate that I am referring to volume here, v we shall be using for velocity if required. So, it will be equal to, assuming all these dimensions dr, dz and d phi to be sufficiently small, then we can write its volume to be nearly equal to dr in one coordinate direction, then r d phi in the other coordinate direction, and dz in the third coordinate direction. So, accordingly we have the volume as equal to r dr d phi dz. This is the volume of this infinitesimally small block. Now, look at the directions. Here the plane which is having its normal in the r direction, that the plane which is having its normal in the r direction, that is this particular one, is being subjected to an heat flux of q dot r, or not heat flux, rather heat transfer rate of q dot r. Through this opposite phase q dot r plus dr is going out. The phase having its normal in the z direction, it is having q dot z entering from this side, q dot z plus dz in leaving from the other side, and the third phase, pair of phases, this q dot phi is entering from this and q dot phi plus d phi leaving out from this particular phase. Now, q dot r plus dr, or if we write this one as q dot at r plus dr position, because here we are talking about an infinitesimally small control volume. This one following Taylor series can be expanded as q dot r plus dou q dot r dou r dr plus dou 2 q dot r dou r dr whole square upon factorial 2 plus the higher order terms. If we neglect everything from second order onwards, then this one can be approximated to be equal to q dot r plus dou q dot r dou r dr. Accordingly, q dot r minus q dot r plus dr can be approximated as minus of dou q dot r dou r dr. Just the same way, following similar methodology, we have already done the same thing for in Cartesian coordinate system. So, I can quickly write q dot phi minus q dot phi plus d phi will be nearly equal to minus of dou q dot phi dou phi d phi and q dot z minus q dot z plus dz nearly equal to minus dou q dot z dou z to dz. Now, we have to write an energy balance over this control volume. So, the same procedure, we are writing a simple energy balance, that is energy coming in minus energy coming out, or rather here we are talking about rate. This is one important difference with thermodynamics. In thermodynamics, you always write them in general form, that is energy coming in minus energy going out plus energy generation is equal to change of energy content. But here we are writing everything in rate form, that is the rate of energy coming in minus rate of energy going out plus rate of energy generation is equal to time rate of change of stored energy content. Now, rate of energy generation is not shown here in this diagram, but we shall be following the procedure that what we have done earlier also. Now, so accordingly energy generation, how we can write it? We can write this to be equal to rate of volumetric energy generation Q0 triple prime into dV. Similarly, change in stored energy content can be written as rho into dV, that is the total mass of this control volume, into specific heat into time rate of change of temperature. So, putting everything together, the rate of energy coming in, now energy is coming in through 3 of the 6 phases, that is q dot r plus q dot phi plus q dot z, and energy going out through 3 other phases, which is q dot r plus dr plus q dot phi plus d phi plus q dot z plus dz plus q 0 triple prime into dV, that will be equal to rho into dV into C into dou T dou T. So, now we can combine the expressions that we have written here. Q dot r minus q dot r plus dr can be expressed as minus of dou q dot r dou r dr minus dou q dot phi dou phi d phi minus dou q dot z dou z dz plus the remaining two terms q 0 triple prime dv. Here there are 3 primes, please be careful while writing, because we are talking about per unit volume. So, and this one we are rearranging a bit, dou t into dv. You can easily expand dv also, I am just not expanding that to save some space. Now, we need to know about the 3 components q dot r, q dot phi and q dot z, or we have to relate them to using the Fourier's law of heat conduction with the temperature gradient in the corresponding direction. Then what we can write? What will be a q dot r? Q dot r as per the Fourier's law of heat conduction will be equal to minus k r into area having normal in the r direction into dou T dou r. What will be q dot phi? That will be minus k phi into a phi into dou T dou phi, that is all? No, it is 1 upon r dou T dou phi, because it is dimensionally not consistent otherwise. There are of course, we can easily got this one from variable conversion, but one thing you can immediately identify, phi being an angle, it is dimensionless, because its unit is radians in SI system. So, but you must have one per unit length scale to be dimensionally consistent, and that is why this 1 by r coming into picture. Another way of visualizing this one is, whenever you are writing this gradient, in the numerator it will always be dou T, but in the denominator it will be the length scale associated with that particular direction. Like in the r direction the length scale was dr, accordingly you are writing dou r. In the phi direction the length scale was r d phi, this one, accordingly you are writing this r dou phi, and similarly in the z direction the dimension is dz only. So, it is much easier to write q dot z will be equal to minus k z a z into dou T dou z. Now, we have to write the areas then. So, it is minus k r a r. A r refers to the area which is having its normal in the r direction, that is I am talking about this particular area. So, what is the dimension of this particular area? How can we calculate? Here I am talking about this particular area. So, what is the, how we can estimate this area? Okay, sorry, this is not the area, the one having normal in the r direction, that is actually on the back side. I was also confused a bit while writing this. So, this is the area that I am talking about. So, you can clearly identify the dimensions of this. You have dz on one side and r d phi on the other side. Similarly, if we want to express the area in the phi direction, then for phi direction, the one that mistakenly I was drawing, this is the one having its normal in the phi direction. So, this area in this case will be equal to dr into d phi, and finally, the area having normal in the z direction. How can you estimate that? So, this is the area that I am talking about. So, what is dimensions? You have dr on one side and r d phi on the other side. So, now let me complete the expressions. Here we had this dou t dou r, here we had 1 by r dou t dou phi, and here we had minus of k z dou t dou z. I am putting it back here in the original expression. So, in the first term we had now minus dou dou r of q dot r. The expression for q dot r we already had, so which is minus k r into r dz d phi dou t dou r, dr outside, minus dou phi of minus k phi. Just write the expression dr d phi into 1 by r dou t dou phi into a d phi outside, minus dou z of, we had minus of k z into r dr d phi into dou t dou z and the dz outside, plus q 0 triple prime into dv. Now you can write the expression. Okay, let me write it in the next line only. So, dv bar is equal to rho c dou t dv bar or dv over crossed. So, now we can easily see which terms we can take out of this of the terms, each of the differentials, like this dz and d phi are independent of r. So, if we take it out, then it remains to be equal to, and all the minus signs we can cancel out. So, it remains dou r of, you have an r inside, r k r dou t dou r into dr d phi dz plus dou phi of k phi dou t dou phi into, outside we have 1 by r, because r is independent of phi. So, it can come out. I think I have written something wrongly in this expression of a phi. Let me try the a phi again. A phi refers to this particular area. So, it is having dimensions of dr dz. I am sorry for making this mistake. While writing this, I just somehow wrote d phi instead of dz. So, I should correct it here, then it becomes dz only. So, it now in outside we have 1 upon r dr d phi dz plus dou z of k z dou t dou z, and again r can come out of this. So, we have r dr d phi dz plus q 0 triple prime. Now, what is your dv that we wrote in the previous slide? Here we have the expression for dv here. So, that is r dr d phi dz is equal to rho c dou t into r dr d phi dz. Now, let us divide the entire equation by this dv, that is r dr d phi dz. Then what we are left with? We are left with, let me write in a proper way, then we have now left with 1 by r into dou r of r k r dou t dou r, because the rest part cancels out, plus 1 upon r square dou phi of k phi dou t dou phi plus dou dou z of kz dou t dou z plus q0 triple prime is equal to rho c dou t dou t. This is the generalized heat diffusion equation in cylindrical coordinate system. Just carefully look at the three terms and try to compare with the one that we have developed in the previous class in relation with the Cartesian coordinate system. Here the first term refers to the heat conduction or heat diffusion in the radial direction, the second term refers to the heat diffusion in the azimuthal direction, and the third one refers to that same in the axial direction. Then we have the traditional heat generation term and the transient term or time rate of change of energy content of the system. And as we have divided everything by volume, so each of the terms basically having dimension of per unit volume or rather heat transfer rate per unit volume. In special cases of isometric or isotropic materials, we have Kr equal to K phi is equal to Kz. So, if we assume an isotropic material plus steady state and no heat generation, then this equation reaches to much simpler form. It is 1 upon r dou dou r of r dou t dou r plus 1 upon r square dou 2 t dou phi 2 plus dou 2 t dou z 2 is equal to 0. And another even simpler form and also very well used form, that is when you are talking about an axisymmetric material or axisymmetric system. Axisymmetric refers to the variation in the phi direction, variation in the azimuthal direction can be neglected. In that case, the dou dou phi part that goes off. So, for an axisymmetric condition, you have this thing left with it. So, this is what we have for axisymmetric situation. We have variation only in r and z direction to be considered, and this particular form of heat diffusion in cylindrical coordinate system is very much well used, because quite often we can neglect the variation in the phi direction, we just have to consider the variation in the r and z direction, and we can reach even simpler situation where we are talking about a purely one dimensional heat conduction situation and the primary direction being the radial one. In that situation, even the z direction is also not there and your equation is even simpler. Then as we are talking about temperature variation only in the r direction, so in that case it will be 1 by r ddr of k dt dr to be equal to 0, r dt dr of 1 by r ddr of r dt dr equal to 0, because as we are talking about one dimensional transfer. So, from partial derivative notation we can easily go to the ordinary derivative notation. So, this is the generalized form of heat diffusion equation in the cylindrical coordinate system. Please try to derive this one just following the method that I have discussed here. Now, let us try to repeat the same procedure for in spherical coordinate system. The spherical coordinate system you may encounter where you are dealing with a spherical kind of object, something like say the fuel storage tank of a space shuttle etc., where we generally have a cylindrical kind of we have a spherical kind of vessel to store the fuels, and a few other scenarios also you may encounter while solving numerical problems later on. So, here we are talking about a sphere and we have got an infinitesimally small volume of that. Look at the coordinate system again. Now, the standard xyz coordinate system is there and here we are changing a bit from there from the cylindrical one. So, if this is your point, then here r refers to the radial position of the point. So, r is just direct distance of the point itself from the origin. Now, once we are taking the projection of this r on the xy plane, that is I am talking about this particular projection, which is the projection of r on the xy plane, then the angle it is making with the x coordinate direction is called phi, and the angle r itself is making directly with z is called theta, or we are denoting them as theta. Here phi is the azimuthal direction, theta is the polar direction. So, r refers to the radial position of this one, that is the distance of the point from the center of the coordinate system. Theta refers to the angle this radius is making with the z direction, and phi refers to, quite similar to the cylindrical coordinate system. If we take a projection of this r on the xy plane, then the angle it is making with the x coordinate system is called phi. So, now let us try to identify the dimensions for this infinitesimally small volume. If this position refers to r and this r plus dr, then this dimension is quite straightforward, it is dr only, because here this particular face or particular line is at a distance r, at a radial location r from the center, this is at a distance of r plus dr. So, we are having a distance of dr along this. Then in the z direction or in the upward direction, what will be a coordinate direction? It is r and its projection of r on the vertical plane or vertical dimensions rather on the z directions. So, that is r into d theta, and to get the final one, we have to talk about the projection of r on the xy plane and the angle phi it is making with this. From here we get this to be equal to r sin theta d phi. So, these are the dimensions for this infinitesimally small control volume. Then its volume should be equal to, in one direction it is dr, in the next direction it is r d theta, and in the third direction it is r sin theta d phi. So, if we separate them out or write sequentially, then r square sin theta dr d phi d theta. This is the coordinate directions, or rather using the coordinate directions and also dimensions or length of each of the edges, we are getting the volume of this infinitesimally small control volume. Now, look at this, it has got 6 faces as usual. So, through 2 of the faces, that is the faces which are having normal in the r direction, it is having q dot r amount of heat is coming from this side and q dot r plus dr leaving from this side. Through the faces having normal in the phi direction, q dot phi is coming through this phase and q dot phi plus d phi is the one leaving from the other phase, and for the last two, q dot theta is coming from the bottom phase and q dot theta plus d theta is leaving from the top phase. So, just following the Taylor series expansion, we can write q dot r plus dr is equal to q dot r plus dou q dot r dou r dr plus dou 2 q dot r dou r 2 into dr whole square upon factorial 2 plus dots, or we can approximate this one to be equal to just q dot r plus dou q dot r dou r dr, neglecting all terms from second order onwards. Accordingly, we can write q dot r minus q dot r plus dr nearly equal to dou q dot r dou r dr. Just the same way, we can write q dot phi minus q dot phi plus d phi will be nearly equal to dou q dot phi dou phi d phi, and q dot theta minus q dot theta plus d theta will nearly be equal to dou q dot theta dou theta d theta. Now, we have to write the energy balance expression. So, just following the earlier principle, the rate of volumetric rate of energy generation can be represented as qg dot triple prime dV, and rate of energy storage can be written as rho into dV, that is the total mass, into specific heat into dou T dou T. So, we can write the energy balance, that is rate of energy coming in minus rate of energy going out plus rate of energy generation is equal to a rate of energy storage, time rate of change of stored energy content. So, energy coming in from the 3 phases, which are q dot r plus q dot phi plus q dot theta, and going out through 3 other phases, which is q dot r plus dr, q dot phi plus d phi, q dot theta plus d theta, plus energy generation q0 triple prime into volume, and this one by rearranging we write rho c dot t into volume dV. Then using the expressions that we wrote from here, we can directly write q dot r minus q dot r plus dr. Actually, I have missed the minus sign here. All of them has a negative sign. So, q dot r minus q dot r plus dr be equal to minus of dou q dot r dou r dr, q dot phi minus q dot phi plus d phi is dou q dot phi dou phi d phi, q dot theta minus q dot theta plus d theta is q dot theta dou q dot theta dou theta to d theta, plus the remaining two terms q0 triple prime dV is equal to rho c dou t into dV. So, now you have to get this three heat transfer rates through each of the phases. So, q dot r will be equal to what? Will be equal to minus k r into a r dou t dou r, just the standard form. But q dot phi, how you can write q dot phi? Minus k phi a phi, and then what about the third one? As I mentioned, you can get it from the coordinate system conversion, or just look at the dimension of the control volume in this particular direction. Like in the r direction, the dimension is only dr, so we have only dr in the denominator. In the phi direction, what is the dimension? R sin theta d phi. So, it will be equal to 1 by r sin theta dou t dou phi. Similarly, q dot theta will be equal to minus k theta a theta into, you have to look the dimension is r d theta. So, it is 1 by r dou t dou theta. Now, you have to get the three areas. So, it is minus k r dou t dou r into the area, this is minus k phi dou t dou phi into 1 by r sin theta into the area, and this is minus k theta into 1 by r dou t dou theta into the area. So, look at the areas. Firstly, the one having its normal in the r direction. So, which one is this? This is the area that I am talking about. So, what will be the dimension of this area? Its dimension is r d theta one direction and r sin theta d phi in the other direction, the one having normal in the phi direction. So, this is the one having normal in the phi direction. So, you have dr on one side and r d theta on the other side, and finally, the one having normal in the theta direction. This is the area that I am talking about. So, it is having dr on one side and r sin theta d phi on the other side. So, we are putting it back here. So, for the first one we have minus dou r of minus k r. So, we have here r square sin theta d theta d phi, that is the area, into dou t dou r dr outside minus dou phi of minus k phi into the area becomes r dr d theta into 1 by r sin theta. So, that r cancels out, dou t dou phi d phi. So, this r can be cancels out from here, minus dou dou z of q dot dou dou theta of q dot theta. So, we have here minus of k theta into the area as r sin theta dr d phi into 1 by r dou t dou theta into d theta. So, here also the r cancels out, then we have the remainder, that is q 0 triple prime into d v bar is equal to rho c dou t into d v bar. So, if we take the terms out suitably from the first one, then of course, all the three from the first three terms the minus sign goes off and we are left with dou dou r of sin theta can come out of this. Similarly, d theta and d phi can come out of this also, but we have r square k r dou t dou r into outside we have sin theta dr d theta d phi plus dou dou phi of, we are left with here inside k phi stays there and we have a dou t dou phi, then what comes out, there is 1 upon sin theta into dr d theta d phi. From the third term, which is dou dou theta of, inside stays k theta and a sin theta also remains now inside and dou t dou theta. Remember, we are writing if we want to take sin theta out, of course we have to differentiate. So, better keep the sin theta inside. So, outside what I am getting here is, we have just dr d theta d phi plus q 0 triple prime. Now, we have to put this dv. What is dv? This is your dv, r square sin theta dr d theta d phi. So, instead of writing the form and making the expression even longer, I am just keeping it in dv form, and in the next line I am dividing everything by this dv, that is r square sin theta dr d theta d phi. So, if we divide by that, then from the first term we are having 1 by r square into dou dou r of r square k r dou t dou r plus the phi term, we are dividing by r square sin theta dr d theta d phi. So, we have 1 by r square sin square theta into dou dou phi of k phi dou t dou phi. From the third term, 1 upon r square dou dou theta of k theta sin theta dou t dou theta plus q 0 triple prime is equal to rho c dou t dou t. Oh sorry, here there should be 1 upon r square sin theta, because 1 sin theta stays inside, it is 1 by r square sin theta. So, this is the form of the generalized heat diffusion equation in spherical coordinate system. Of course, looks quite complicated, but if you try to derive that just the way I have done, then you will get the hold of the entire thing and it will not be very difficult for this. Again, quite often we may have to deal with isotropic materials. So, if we try to develop a simpler form, let us put a few assumptions. So, let us write say steady, then isotropic material and no heat generation. In that case, the k can be taken out of these brackets. Let us say isotropic and also constant properties. In that case, k r, k theta and k phi are equal to each other, and we take them out of the differentials. So, the equation becomes 1 by r square dou dou r of r square dou t dou r, plus it is convention to write the theta term before phi simply, and so it is 1 by r square sin theta dou dou theta of sin theta dou t dou theta plus 1 by r square sin square theta dou dou phi of, or just as k phi has come out, we can directly write dou 2 t dou phi 2 is equal to 0. And if we are dealing with a 1D or 2D heat transfer situation, it can become even simpler. Like if we are talking about just a plain 1D heat transfer situation where radial direction is the one of importance, then this becomes even simpler. 1 by r square ddr of r square dt dr to be equal to 0. This kind of equation we shall be dealing in the next week, when we shall be talking about purely 1D heat conduction situation. So, we have now developed the heat diffusion equation in all the 3 coordinate directions, that is starting with the Cartesian, we have developed it for cylindrical and spherical coordinate system as well. And I hope you have got the procedure, or at least if you have followed it carefully, then you have got the procedure how we have developed this, but my request is try to derive the equations on your own, so that you do not face any problem later on. But at the same time, I should also mention that quite often, at least as a part of the course, you do not have to deal with the equations or such big form of equations. At least you always will be using only 1D or 2D form of the equations, but still it is always good to know what is a basic equation looks like, and that is what we are given here. And the discussion in relation to the boundary condition that I have done for with regard to the Cartesian coordinate system, they are also valid here. The same way we can easily imply the Dirichlet, Neumann or convective kind of boundary condition in cylindrical and spherical coordinate system as well. You just have to remember the expressions for this heat fluxes or powers, heat transfer rates, and like if you are talking about a Dirichlet boundary condition, it is very simple. At a given location, the value of temperature is given. If you are talking about a Neumann boundary condition, then basically this power is given, because the temperature gradient dou t dou r, dou t dou phi or dou t dou theta, or maybe just q dot r, q dot phi or q dot theta, they are given. So, from there we can get the idea about how to solve the temperature. Or if you are talking about any convective boundary condition, then the power expressions that we have written here, that conduction heat transfer rate will be equal to the corresponding convection or radiative heat transfer rates. So, accordingly we can apply any kind of boundary condition depending on whatever kind of problem we are dealing with. So, that takes me to the end of the second module. I was tempted to solve a few numerical problems here, but I am not doing that, because as we have developed only the generalized form of the conduction or heat diffusion equation, corresponding numerical problems may be quite difficult to solve, as we have to deal with either very complicated equations, or we may have to simplify the equations. Now, in the next week we shall be talking about 1D heat conduction, where we shall be developing, or I should say we shall be reducing these equations, all the 3 versions, into their corresponding one dimensional counterpart, and therefore, it will be much easier to deal with corresponding numerical problems. So, I shall be doing that only in the next week. But in this week what we have done, if we want to have a brief summary, we started with a generalized form of the Fourier's law of heat conduction, then talked in detail about thermal conductivity as a property, and also introduced to the thermal diffusivity. Then we developed the heat diffusion equation in Cartesian coordinates. Today we have developed the same equation in curvilinear coordinates, both spherical and cylindrical coordinates, and also we have discussed about 3 possible kinds of boundary condition that we can encounter while solving the heat diffusion equation. So, I would like to thank you for your attention while listening this. Please solve the assignment problems, try to solve a few problems from the book, and also I request again, try to develop the equations on your own, so that you do not face any problem later on. Thank you very much.